Hi 254. In this video we're going to discuss the little bit of 11.4 that we have to finish. So the first thing I wanted to do is do a couple examples of calculating a cross product using the determinant of a matrix. Remember I set this up with you how we're going to take a cross product of two vectors, u cross v, by doing the following 3x3 matrix, and we'll find its determinant. That's the vertical bar notation we have going on right here. And notice we have ijk, and then we have u1, u2, u3, v1, v2, v3, where those are the components from each of the individual vectors u and v respectively. And then we follow the process of I times determinant of the 2x2 minus j, determinant of this 2x2, and plus k, determinant of the resulting 2x2. And remember, each of these small 2x2 matrices are found by eliminating the row and column that either I, j, or k live in. Okay? And remember to alternate the sign, positive, negative, positive. So let's try an example. And this one I just chose from the textbook, so it's 11.4, problem number 30. So let's find a vector that is in fact normal to these two vectors that I have given here, 1, 2, 3, and negative 2, 4, negative 1. Let me make sure my pen's not going to be like super wide like a paintbrush. There we go. Okay, so if we want to find a vector that's going to be normal to each of these two vectors, remember the cross product is giving us a vector that is going to be pointing using the right-hand rule orthogonally to each of the original two vectors, right? Remember, we use the right-hand rule to figure out how this vector is going to point, and it's going to be orthogonal to each of the original two vectors. So what we have to do to figure out the cross product here, to figure out a vector that's orthogonal to 1, 2, 3, and negative 2, 4, negative 1, is to figure out the cross product, right? So we do 1, 2, 3, cross that with negative 2, 4, negative 1. And again, I can set that up by constructing this I, j, k, and these are notations like that. And I do 1, 2, 3 here, components of the first vector, negative 2, 4, negative 1, components of the second vector. And now I just go ahead and write, let's see, I need determinant of the resulting 2x2 when I take away I, right? I is in first row, first column. That vector is 2, 3, 4, negative 1, right? That's these four here, minus, because we alternate signs, let's see, the next one's going to be j, and when I eliminate j, it's in the first row, second column, so I have 1, 3, negative 2, negative 1 left. And then plus determinant of what happens when I take away k, let's see, first row, last column taken away, I have 1, 2, negative 2, 4. Okay, and now we just remember do the 2x2 determinant by using this kind of property here. We do this like crossing kind of thing like that, right? Okay, so we're going to do 2 times negative 1 minus 3 times 4, and that'll be what we have for I. And then we'll do the same thing for j and for k, right? Okay, I'll let you finish those little manipulations here, but at least let's make sure we have the answer correct. So let's see, negative 2 minus 12 is going to be negative 14. I, right, minus, what do we get for j? Let's see, negative 1 minus a minus 6 is negative 1 plus 6, which is 5, but there's a minus out front, remember, so don't forget that. Plus, let's see, 4 minus a minus 4 is 4 plus 4, which is 8. Okay? And so that gives us a new vector. Notice, remember the cross product gives us a vector, not a scalar, right? So as expected, we have a vector as a result. Let's just discuss the one application that's mentioned in this section, and that's the application of torque, right? The definition for torque is here. The torque or twisting effect is the tendency of a force to rotate an object about an axis, a pivot, or a fulcrum, right? And the example in your textbook that they give is a wrench like this, right? Where you actually have the idea of there being some kind of lever, right, or arm or something like that, and there's going to be some kind of a force applied to it at some kind of an angle here, right? Okay, so we've got this arm right here and a force F of a certain magnitude and direction, right? Imagine this is like the effect of you were going to try to loosen a bolt or something using a wrench, and you're going to push down on the end of the handle, and you're going to push at a certain angle, right? Your arm will make a certain angle, and so the result here actually has an effect of producing a vector that gives you the twisting effect of this wrench either tightening or loosening the bolt, right? It's either going to say the resulting action, the cross product, the resulting vector that you produce is either going to be a vector pointing in this direction here, right? Or pointing the opposite direction out. And again, depending on what kind of screw it was or whatever, that would be tightening it or loosening it or threading it or not threading it or whatever. It depends on the situation. But the idea is still there, that we're going to basically take this vector, which is the arm of this wrench, kind of an idea, and then we're going to cross it with the vector, which is the force vector here, and the result will be that torque vector. Okay? So let's see where we're at here. So torque is the vector tau, which is equal to r cross f, where f is the force vector being applied to the point P, which is at the head of vector r equals OP, right? And that's the same for the picture I just showed you in the textbook, right? And the force vector f is, by the way, applied at an angle of theta, right? And of course, the magnitude of this torque vector is just the magnitude of that cross product with its usual definition, right? Magnitude r, magnitude f, sine theta, right? So if we go back to our picture here, right, we can see that to figure out this tau vector right here, yes, we can just cross this vector r with vector f, right? And if we wanted to know just the magnitude, we would need to know the angle right here, yes? And of course, the effect of this force vector on this magnitude, or this vector here, the arm length kind of vector, the resultant vector is completely affected by what kind of an angle this force acts on that lever with, on that arm with, right? Okay, so that's why theta it matters in terms of producing a different value for the magnitude of the torque vector. So let's try an example. And we'll see, let's try 11.4, problem number 34, and let's see. So in this problem number 34, again in section 11.4, what we want to try to do is figure out the torque when we know what the wrench would be, how it would be described, right, as a vector, as well as the force that's going to be applied. So let's see, number 34. We have for number 34, our vector r is given in ijk components, but I'll write it here with the bracket notation as 1, -1, 2. And we know our force vector, capital F, is 10, 10, 0. Okay, now they've just asked us for the torque, right? And they haven't said specifically if they want are wanting a vector or a magnitude of that vector, but let's just go ahead and find both of them, right? We'll find the vector that represents the torque, which includes magnitude and direction. And so to do that, remember we say that tau is equal to r cross f, right? Which again is just doing what? A determinant of a 3x3 matrix, I, j, k. Sure they have the hats because they are in fact vectors. This is 1, -1, 2, 10, 10, 0. And when I do the determinant of this 3x3 matrix here, I'm going to get, let's see, what do I get for I? I'm going to get 0 times -20, so or 0 minus, sorry, 0 minus 20. I'm really tired right now. Okay, minus, let's see, when we do j, we take away this column and this row, so I'll get 1 times 0 is 0 minus 20 again, so minus a minus 20, however, would be plus 20, j. And then for k, what do we get? Last column, first row, I would get 10 minus a minus 10, which is plus 20. Okay, let me make sure I did the I one correct here. 0 minus 20, good, okay. So there is the resultant vector, that would be the torque vector, -20, 20, 20, right? Again, another way to write this would be 20 times -1, 1, 1. And from here you can actually easily see what the magnitude of this vector tau is, right? What the magnitude of the torque is going to be. It would be what? 20 times the magnitude of this vector here, times the magnitude of -1, 1, 1, right? Which is 20 times the magnitude of this vector is square root of 3, right? And I don't think they give us any. They don't have any units in that problem, so we don't have any to apply, right? If there were units, we would apply whatever units were given in the problem. That finishes out 11.4. You can move on to the video for 11.5.